Students, are you able to see the PPT?
Yes, sir.
Okay, so in last lecture, we discussed about the input impedance and current gain of Darlington pair, right? These two are important topics which we discussed yesterday. Now we will see the voltage gain. Okay, so voltage gain of Darlington pair is given by AV. It is equal to AV1 multiplied by AV2, where AV is the voltage gain of Darlington pair, full Darlington pair, total Darlington pair, and AV1 is voltage gain of Q1 transistor, right? And for that we will use the exact analysis. For Q1 we are doing the exact analysis, and for Q2 we are doing the approximate analysis. And AV2 is the voltage gain of Q2 transistor by using approximate analysis. So first we will calculate AV2 of Q2 transistor. So in case of voltage gain of exact analysis and approximate analysis, if you remember, the formula is same for the voltage gain in both the analysis. Okay, right. So we will find out first voltage gain of Q2. So voltage gain of Q2 is given by current gain of Q2 AI2 multiplied by RL2, that is the load resistance of Q2 divided by input resistance of Q2, right? This is the formula. If you recall the voltage gain, how voltage gain you write? Voltage gain is AI by Ri. This, right? Same thing here. Output resistance here is RL, whatever is the load resistance. Okay. Now in this expression, what I have done, I have written it like this: 1 minus AV2 left side, and same I will subtract this also from 1 minus AI2 RL2 RI2, right? So this I can do. This I have done only for simplification. Suppose here it is X and here it is Y and both are equal. So if I am writing it like this, subtracting X from 1, so if I subtract Y from 1, then also both will be same. So same thing I have done here. 1 minus AV2 and 1 minus this expression. And now 1 minus AV2 is equal to, I will simplify this one. So in the denominator I have Ri2. Here I have Ri2 minus AI2 RL2. Now Ri2, this expression already in last, we already calculated this one. Ri2, it is HIE plus 1 plus HFE RE, where 1 plus HFE you can write it as a HFE. So now you see here Ri2 I have written as HIE plus AI2 RE. So this RI2, this I have written as HIE AI2 RL2 because RE. What is the meaning of RE? RE is this. This is RE, and this is nothing but this is the load RL2, load of the second transistor. So same thing here. I have written RL2 in place of RE2 and minus AI2 RL2. This part. Okay. So this part and this part will be cancel out, and we will get HIE divided by RI2. So 1 minus AV2 is this, and from here you will get the expression of AV2, and this is equal to 1 minus HIE divided by HI2. This is my one expression. Now I will calculation for voltage gain of Q1 transistor, that is AV1. So AV1 is equal to current gain of one transistor, load resistance of first transistor and input resistance of first transistor, this. And in left side and right side, whatever expression we are having, these expression I will subtract it from 1. So I will get 1 minus AB1 and 1 minus AI1 RL1 by RI1. And now I will somewhat simplify this right hand side. So here I will get RI1. In numerator here I will get RI1 minus AI1 RL1. Now RI1, how I can write RI1? HIE plus AI1 RL1. I can write it in this way. Already you can see here. This RI2, how we have written RI2? HIE AI2 RE. Same way RI1, how we have written? HIE AI1, and this is your load resistance, that is RL1, first transistor load resistance. Okay, if I simplify this and this will be cancel out, and I will get finally AV1 is equal to 1 minus HIE by RI1. This is my 12th expression. Now overall voltage gain, AV1 multiplies by AV2. So AV1 is this. So this I have written here. And AV2 is this. So this part I have written there. Multiply both the things. Okay. Now in a common collector configuration, HIE by RI, this HIE input resistance, right? What is its value? HIE value, if you recall, it is 1100 ohm standard value, right? Divide by input resistance. Input resistance is very high in case of common collector. So the overall term HIE divided by RI is very small, because here 1100 ohm will be divided by very high input resistance, because in common collector input resistance is very high. So this term is very small. So if this term is very small, then you can neglect this term. You can neglect this term. So we get only this 1 multiplied by 1. So we are getting voltage gain approximately 1. So for a Darlington pair, voltage gain is approximately equal to 1. Okay. Okay, now we will see the output resistance of Darlington pair R0. So output admittance, we can express it as a Y0 is equal to 1 by R0. Now we know that R0, this is the expression of R0. You can see here. H parameter R naught. See this R naught. R naught is RS. RS is the resistance of source, voltage source, plus HI divided by RS HO plus delta H, where delta H is H naught HI minus HR HF. So we will take this value R naught. So you see this R naught is this, right? Same expression I have written here. So I will write it in terms of admittance. Admittance is Y naught. So Y naught is reciprocal of R naught. So I will get this term. Okay, simply this I will do the reciprocal of this. So I will get this term. Now I will split this in three terms. This is first term, HORS divided by HI plus RS. This. Okay. Then this is my second term. You can see here HOHI by HI plus RS. And this is my third term. So you see here minus HF, HR, HI plus RS. Okay. So how I got this? Simply output admittance Y naught is equal to 1 by R naught, whereas R naught already we know for a H parameter model R naught is this, and I have written it in terms of Y naught, means reciprocal of that, and I have splitted these in three terms. That's all. Okay. So this is my first term, this is my second term, and this is my third term. So now you just see the second term, this one, HOC HIC divided by HIC plus RS. So here HOC, the standard value of HOC is 1 by 40 kilo ohm. Already I have explained, I told you this. HIC standard value is 1100 ohm. Right? So the numerator part, HOC HIC, is very small. You can see 1100 ohm divided by 40 into 10 raised to power 3 ohm. So this will be very small. So numerator is very small, and this small numerator is divided by this value. So final value will be even smaller than that. So this second term is very small. Okay, so we can neglect the second term, right? We can neglect the second term. Now if you come to the first term, HOCRS by HICRS, this is also approximately equal to HOC. If you put these values here, HOCRS, HICRS, then you will find that it is approximately equal to H naught, where RS is the source resistance of your source, which is internal resistance of the source, which is very less, around 100 ohm only, right? So this first term will be represented by H naught, second term will be neglected, and third term we will keep as it is. So we will get an expression Y naught is equal to HOC minus this term, or Y naught is equal to, now you see HOC and HOE are equal. Standard values are 1 by 40 kilo ohm. So here in place of HOC I have written HOE. Okay. Now here you see this minus sign. I kept here plus and minus I have taken here. I have taken here so that this minus HFC, it will be equal to 1 plus HFE or approximately equal to HFE. Because 1 plus HFE value is 50. So 1 plus 50 is 51. So it is approximately equal to 50. So in place of this, I have written 1 plus HFE here. 1 plus HFE. Even I can write only HFE also. Now HRC, reverse voltage gain of common collector. If you recall, HRC standard value is 1. So this I replace it by 1. Okay. So this whole term will become 1 plus HFE. In the numerator, in place of IC, we have written HIE. So this is the expression of output admittance, right? This is the expression of output admittance. So Darlington pair is important. Sometimes even simple calculation of the values can also be asked. If HOE value is this, H parameter values are these, then find out the input impedance or output impedance of Darlington pair, right? And many times even the simple derivation of the expressions are also asked, right? So in this, the important is your first one is important, current gain. The second one is also important, input impedance. So you should go through with all these. Okay. Now another important topic which can be asked in the theory is like a frequency response. It can be frequency response of a BJT or frequency response of RC coupled transistor. This can also be the question, frequency response of RC coupled transistor or simply frequency response of a BJT or effect of coupling capacitors. Effect of coupling capacitors, right, on the voltage gain of a transistor. So question can be asked in this way and you have to write the theoretical answer for this, right? So if these type of questions are there, then what you can do, you draw this diagram, right? You draw this diagram. Here in y-axis, it represents voltage gain. X-axis represents the frequency, and this is the frequency curve. This is the frequency curve. Okay, this maximum value of this voltage gain, we write it as a AV. Now the value where the AV is 70.7% of the voltage gain, that is 0.707 AV. At this point is the 70.7% of voltage gain. So at this point, what is the frequency? So this frequency is denoted as FL, right? Low frequency. This is FL is low frequency. So at FL, the voltage gain of the transistor has become 70.7% of maximum voltage gain, 70.7% of maximum voltage gain. So that frequency point is denoted as FL. So 70.7% means it is 0.707 of AV. Same way, this side you will find same type of point there, and this frequency is called as FH. So FH is a higher frequency at which the voltage gain becomes the 70.7% of total voltage gain. FL is the lower frequency at which the voltage gain will become 70.7% of total voltage gain. Right. So these frequencies are defined are denoted as FL and FH. Generally, the value of FL is 15 hertz and FH is in this 17 kilohertz. It is in the range of kilohertz. And this curve, which is in left hand side of FL, is called as low frequency region curve. Okay. And the curve which is at the right hand side of this FH is high frequency region curve. Okay, it is high frequency region curve. And here in between this FL and FH, this is the mid frequency region curve. Okay, these are the curve. So if somebody asks if there is a question on frequency response of BJT or frequency response on RC coupled transistor or effect of coupling capacitors on the frequency response curve. So first you start with this curve. Then you draw this circuit diagram. Right? This is RC coupled transistor amplifier. So this is a NPN transistor. At the base terminal, this is base terminal. Here we have connected one capacitor. We call it as CC1. And here one voltage source is connected. Voltage source of voltage Vs. So Rs is its internal resistance of this voltage source. Now there is one RC resistor which is connected at the collector terminal of the transistor, and the second end of this RC resistor is connected to VCC, and there is one resistor RE, emitter resistor, connected at the emitter terminal. There is a capacitor CE which is connected in parallel to this RE resistor. Now you find here one capacitor CC2, right? And load resistor I have connected here at this end and between the ground. And across the load I am taking the output. So here C1 and C2, CC1 and CC2 are called as coupling capacitors. So they are used. Why they are used? What is the function? CC1 is used to couple the source voltage with the transistor. CC2 is used to couple the output of a transistor with the load, and CE is used as a bypass capacitor for RE resistor. Okay. So now see, if you don't have here load, you just remove this load. Don't take the output across this. Now what we can do? From this CC2, I will connect this to another transistor. Right here, this is RC. This is RE. Here there is one capacitor CE, this is CC, and here we have connected some load resistor RL, and we are taking the output here. So here what happened, we have removed this RL, because if you use one transistor, so it is used as an amplifier, so it will amplify the strength of Vs, but there is the possibility the amplified strength is not sufficient for our application. We want to again amplify this. So we have connected the second transistor here for the further amplification. So here you see, this is the first stage. This is the first stage of an amplifier. This is the second stage of an amplifier. And how it is connected? It is connected between by using this capacitor, and here we have some resistance RB. So here the stage 1 of the amplifier and stage 2 of the amplifier are connected together by using R and C, by using resistor and capacitor. So this is also called as RC coupled circuit here. So frequency response of this, and for single amplifier, that curve I have shown here. So you draw this circuit diagram. You mention that CC1, CC2 are coupling capacitor, CE is bypass capacitor. Then first we will see the effect of coupling capacitor. The coupling capacitors are used in amplifiers to block DC of the signal and to allow AC part of the signal. Means here this capacitor we are using so that we should allow this AC part of the signal to input to this transistor for the amplification. And here we are using the DC voltage VCC for the biasing purpose. So it will block this DC to go outside. Okay, so this is the purpose here. Same way, at the output side, whatever DC voltage is there due to for this biasing, it will be stopped by this coupling capacitor number 2. Right, so DC voltage will not pass through this, only the amplified AC signal will be passed. Okay, so this is the purpose of this coupling capacitor. But this coupling capacitor will affect the performance of a transistor. Okay, so here I have written what is the purpose of coupling capacitor. Then since we know that reactance of a capacitor is given by Xc is equal to 1 by 2 pi C, or Xc is inversely proportional to F, frequency of the operation. So coupling capacitor offers very low resistance in mid frequency and high frequency regions. So see here, if the frequency of the operation is more, frequency is more for a transistor, then this Xc, capacitive reactance, will decrease. So if you see this frequency response curve, here we are having 3 regions. One is low frequency, one is mid frequency, one is high frequency. So in mid frequency and high frequency region, where the frequency is higher, in these regions, the capacitive reactance of the coupling capacitors will be very low, and they are considered as a short circuit. Right? So you see here CC1, I am showing by a short circuit. CC2, I am showing by a short circuit. Okay. Now bypass capacitor, this is also you shorted, because at high frequency and mid frequency range they offer very less resistance. This is also short. So RE in parallel with short circuit. So RE will be bypassed. So current will flow through short circuit capacitor. That's why this capacitor is called as bypass capacitor. It will bypass RE. So in low, so now you draw this circuit diagram, right? This is your second figure. where you show CC1 short circuit, CC2 short circuit, and here you remove the RE. So in low frequency region, coupling capacitor offers, okay, now, so there is no effect of the coupling capacitors at when our transistor is operating in mid frequency region or high frequency region. Now we talk about the low frequency region. In low frequency region, the coupling capacitor offers some resistance, because already we know Xc is inversely proportional to 1 by F. So if frequency is less, then this reactance, capacitive reactance will increase. So now coupling capacitors will offer some resistances. So if they will offer some resistance, then there will be definitely some voltage drop across these resistance. Okay, there will be voltage drop across these resistance. Okay. Now what is the effect on the bypass capacitor? So bypass capacitor is connected in parallel to RE. In mid frequency and high frequency region, the reactance offered by bypass capacitor is very less and it is considered as a short circuit. There is no voltage drop across short circuit, so the dip in the voltage gain in high frequency region is not due to bypass capacitor. But in low frequency region, bypass capacitor offers reactance. So you can see here XCE and RE, two resistors, it looks like they are in parallel. So there will be overall some resistance will be there, and if resistance is there, then there will be some drop. So voltage will drop and finally V out will decrease. So voltage gain will decrease. So what is the conclusion here? The dip in voltage gain in low frequency region is due to the coupling capacitors and bypass capacitors. So you see there in this figure, in the low frequency region, there is a decrement in the voltage gain. Voltage gain is decreasing when you are decreasing this frequency of the operation. So if you are decreasing the frequency of operation, then the reactance offered by the coupling capacitors will increase, and if it will increase, then there will be more voltage drop across these capacitors, and finally the voltage gain will decrease. So in low frequency region, the decrement in the voltage gain is due to the coupling capacitors and due to the bypass capacitor. Now we see the internal capacitance. So already we discussed earlier also, whenever there is a PN junction, then a capacitance will be formed internally. So here in a transistor, you can find internal two capacitance. One is CCB, the capacitance between collector and base. Another is CEB, capacitance between emitter and base. So at low frequency, when frequency operation is low, the capacitive reactance of CCB and CEB will be very high, because Xc is inversely proportional to frequency. Frequency is low, then the capacitive reactance will be high. So this high capacitive reactance is considered as an open circuit. So you can see here there is an open circuit. So there is a no impact, right? So due to the open circuit internal capacitors, there is no effect on voltage gain on the amplifier in low frequency region. But in high frequency region, what will happen? In high frequency region, they will show some reactance, right? And thus there will be shunting effect, and finally the voltage gain will decrease. So what you can conclude, internal capacitors are responsible for decrement in voltage gain at high frequency region. Okay, so if you recall this curve, voltage gain and frequency curve, this is your voltage gain AB. On y-axis we are taking the frequency. So this decrement in the frequency here, decrement in the frequency in this low frequency region, and the decrement of the voltage gain in this high frequency region. So you should very clearly explain why this dip is there. Okay. So internal capacitors are responsible for decrement in the voltage gain at high frequency region. So here the responsibility is of internal capacitors. Internal capacitors which are formed between collector emitter and base. Not collector emitter, collector and base, and emitter and base. Now in this low frequency region, this decrement is due to coupling capacitors. To coupling and bypass capacitors, right? So these all things you have to explain. Okay. Okay, so I stop here, and Monday I will take the analysis of JFET. Okay, that part I will revise. And tomorrow I will try to send the notes to you. Tomorrow or today after tomorrow I will be free in these 2 days. Then I will send.